Good afternoon, everyone. My name is Han, coming from Northwestern University, Civil and Environmental Engineering. Really appreciate this opportunity to give a talk about my current work. Today, I'm going to talk about one novel adsorbent, which I call it a Quampool graphene ball. And we hope to use that to adsorb emerging contaminant from water rapidly and selectively. So as we all know, like every day we have thousands of chemicals manufactured, used, and discharged from industrial and residential area. And unfortunately, those chemicals cannot be completely removed from the traditional water treatment technologies. And as a result, you can see that many of them can be detected in the surface water and groundwater. And we know like some of them have potential negative effect to different organisms as well as human. So far we have like many technology can potentially remove those emerging contaminants from the water. Among them, adsorption is one of the most favorite one. And amongst all the adsorbent materials, and active carbon is one of the most well-used materials. However, although it's well used, we still find a couple of shortage, couple of limitations, such as it is very sensitive to natural organic matters, and the adsorption process is very slow, I mean GAC, and also the cost of regeneration is very high. Therefore, we're still looking for some robust adsorbent which is better designed for the emerging contaminant in a realistic, in a very complicated water environment. Graphene is actually one of the most popular topic in the last 20 years. And so far as we know, it has a very attractive electrical, optical, mechanical, and chemical properties. The environmental application of the graphene or graphene oxide is actually have been studied briefly. And what you can see, the graph on the left, some people propose there are a couple of adsorption mechanism, and we have very strong sorption affinity for different kind of organic contaminants. However, its capability is limited by its nature. And what you can see on the right, because like graphene or graphene oxide in nature, they exist in 2D sheets. So they intend to stuck together. As a result, the surface area got reduced and its efficiency got limited. Therefore, to further use this as environmental adsorbent, we need to do some engineering work. So here is actually like to put graphene or graphene oxide into 3D is a very good strategy. So what you can see here, try to imagine like by the end of the quarter or semester, you have a lot of like assignment, homework, midterm, finals, all the paperwork, and they can stack together very easily. However, if you take them like out piece by piece and make them like Quampool paper ball and throw them into your trash can will be full so easily. So we hope to use this concept to develop a stacking resistant Quampool graphene ball, CGB, and use that as an environmental adsorbent. So the synthesis method is kind of like simple. We using the spraying technology. What you can see here, we use a nano spearhead, which can generate like thousands of aerosol. Each droplet contain many graphene oxide nanosheets, and we give a little bit of heat, and we remove all the solvent part, and those nanosheets will self-assembled and form the Quampool graphene ball, and we use it to adsorb all different kind of like contaminant. So in this talk, I will briefly go through the physical and chemical property of the CGBs, and we also investigate the adsorption isotherm and adsorption kinetics of CGB. And eventually, we will investigate a little about the effect of the environmental conditions such as NOM. So let's start briefly with like some beautiful like Quampool ball SEM picture. What you can see from the figure A and B, Like the CGB we generate is just look like the crumpled paper ball, and the size is about like 1 to 2 micron, the diameter, and also the figure D is the nitrogen adsorption, desorption, and analyze. And from that, well, you can see like we have the surface area is about 180, is 6 times less than the GAC. And also, like we analyze the pore size distribution, which give us like ORCGB is a mixture of the mesopore and the micropore. And also we giving some analysis by XPS. Actually, we did the FTIR and also Raman spectrum also. The conclusion is similar. So ORCGB is more look like graphene oxide instead of graphene. And then among all different kind of like emerging contaminant, we select 8 model, which basically on our one of our previous like research, we collect all different water sample from Illinois and Wisconsin, and many of them show up in the water sample. So which means they are widely distributed and they are kind of like very stable in the nature system. So looking at the chemical structure, well, you can see like there are some like a similarity. For example, most of them contain like carbon-carbon double bond and all aromatic ring. Only one exception I just want to mention is the sucrose. Actually, it does not contain any carbon-carbon double bond, which is very important characteristic, which I will discuss later. So first, we just do a very traditional way to study just using 2 different models, try to fit the adsorption isotherm. And we figure out Lechmere model fit better. And we propose couple of like adsorption mechanism. For example, the hydrophobic attraction and pipeline interaction. And also, as I mentioned, our adsorbent more look like graphene oxide. On the surface, they are contain a lot of like oxygen contained functional group. And we also think those oxygen contained surface group contribute to the adsorption process. For example, like the hydrogen bonding and the electron donor acceptor interaction and so forth. And then we use the QM, which in the model, which represents the maximum adsorption capacity. And we use the QM of our CGB and compare to the GAC. On the left, what you can see, like we kind of like cut the square into 2 triangles. Those points located on the top triangle, meaning like it is more favorable in our CGB. And those points on the bottom triangle, meaning like it's more favorable in our GAC. By looking at this graph on the left, what you can see is kind of like 4 of them. It's kind of 4 of 8 is more favorable in our CGB. So it's kind of like comparable. However, this figure on the left is actually basic on the mass. But however, if we kind of like, if we try to normalize everything by the surface area, which prove like our CGB have more favorable surface, well, you can see on the right, 7 of 8 emerging contaminant we choose is more favorable in our CGB, except as I mentioned, the sucralose is not that favorable in our CGB. And next, we kind of investigated the adsorption kinetics. Although we lasted the batch experiment for 24 hours, but I can give you a very brief conclusion by only show you the 15 minutes result. For our CGB, what you can see, after 15 minutes of the contact, 7 of 8 emerging contaminants we choose reach more than 90% of the removal. Only the sucralose behaves not that good. In comparison, the GAC is the adsorption process is relatively slow at 15 minutes. Like the adsorption is not very obvious. In the later study, we figure out it's taking more than 6 hours to reach its equilibrium. So overall, the CGB show like more rapid adsorption than GAC. And then we investigate the effect of the NOM. So on the right, what you can see is kind of like the adsorption isotherm of 8 individual contaminants. And the red bar is the CGB, and the blue bar is the GAC. And for each bar, we're trying to play around with different kind of NOM concentration. So what you can see is actually NOM have very little effect on the adsorption behavior. Even at a very high concentration of the NOM, the adsorption capacity only reduced by maximum about like 15 to 20%. In the opposite, the NOM have very large effect on the GAC behavior. So if we consider the interruption of the NOM, ORCGB can perform better than the GAC in most of the emerging contaminants we choose, except the coffee and the sucrose. One more thing I need to mention is about we choose the Swanee River formic acid as the model of the NOM. So the 10 milligram per liter is about 5 milligram per liter DOC is a typical level for the surface water. At this realistic level, what you can see is negligible effect on our CGB performance. In the opposite, the GAC is got impacted a lot. So conclusion, summary. So our CGB displayed greater adsorption capacity than GAC, and it also show a rapid adsorption process. And eventually, we can see like our CGB adsorption is not negatively affected by the NOM. Due to time limit, I didn't have time to talk about the others, but it also performed relatively stable in all different kind of like environmental conditions. That's it. Thank you very much. I'm open to all kind of questions.
Great, thank you, Han. We do have time for questions.
I don't have any at the moment.
Does anybody have a question that they would like to ask?
Here we go. Why do you think NOM didn't have any effect on CGB absorption capacity?
So one of the things we kind of like suspect is because of the difference in the pore structure. As I mentioned, like our CGB have a mixture of like mesopore and macropore. So which the pore size is much more kind of like bigger than the GAC. In the opposite, what you can see like the GAC, the pore size is kind of like a micropore dominant. So it's in the other word, like the NOM, they are very large molecule. They are very easy to block those like a small pore size and interrupt the adsorption behavior of the GAC. But in the opposite, our CGB is not affected a lot because of different pore size.